All right, good morning, everyone, and welcome to the last day of this program. I hope you enjoyed being here and the discussions. So we are delighted to have Professor Hugues Chaté from Sakle?
Yes.
Yeah, from CES Sakle. And he is going to talk to us about Vicsek model and update on it.
Thank you, Sumantra. Okay, it's a pleasure to be here. It's middle of the night for me, and I'm feeling okay. I hope you do. Thanks for coming on a Saturday. You know, when I offered, what happened is that I was invited to next week's meeting, and when I realized this one existed, so I wrote to the organizers, can I participate? And then I thought I could come earlier, but in the end, it turned out difficult. So in the end, I end up here, tying you up on a Saturday. Okay, so, and also I'm going to talk about rather basic things, which is a bit unfortunate since this is the end of the program. We'll go back to very simple active matter models, mostly the Vicsek model, in fact. I will say a few things of the sort that this also is true for many other kinds of models, but if you don't believe me, you can interrupt anyway at any moment, right? And it's roughly 2 parts, and I'm not sure where the middle of the 2 parts will fall, so we'll see before coffee break, after coffee break, etc. We'll see. And so, well, first of all, anybody has not heard about the Vicsek model in this room? Okay, we have a brand new person here. Yes. Okay. So I will go to the very basic things, but if it's too fast, you can, in particular, stop me. Okay. This is supposed to be running also and hypnotize you, but it's not running now. Okay, so if you don't fall asleep, you will understand what this movie is at the end. It's just here because it's nice. Okay. And this is a simulation of a Vicsek model, by the way, with fancy coloring, and there's a little, yes. Do you notice something here? The way I didn't realize, there's a little white circle here, okay? This is not a mistake of the font here. This is a little obstacle in the flow, so to speak, which is causing this interesting dynamics. Okay. So I think I can, so first of all, before I forget, the first part is a collection of, I mean, the beginning is very classic stuff that I did some years ago now, but the more recent part has been done by these gentlemen here. That's the young people who did the work as usual, and these are the older people who did some of the work. Okay? And of course, I didn't do anything. And so, in particular today, we'll see the work of Yuduan. There's a young Chinese guy who is now in Göttingen working with Benoit Mao, who was my student. You'll see that. Okay, so active matter, I think I can skip after 2 weeks or whatever it is. Objects, it's made of constituents, some of them at least, that consume, transform energy into mechanical work, and that produces interesting collective properties, and that's what we try to understand. And because this is out of equilibrium in the bulk of the system, from my viewpoint, rather generic way of being out of equilibrium, you can expect interesting phenomena, and this is different from applying a field externally or something like this, okay? And here, 2 things you should know, and we'll focus on one today. You expect also new collective phenomena not possible in equilibrium, in particular, true long-range orientational order, we'll see that, in 2D, emerging from the spontaneous breaking of continuous symmetry, rotational symmetry. Another one, which is very famous these days, is the possibility of having phase separation between particles. You know, they phase separate into a dense microscopic cluster and some residual gas without explicit attractive attraction. So that's called, motility-induced phase separation. So these two phenomena studied in depth on very, very simple models are some of the most spectacular manifestation of new collective behavior in active matter. Okay, so long-range orientational order in 2D, it is, if you've had StatMech courses, you should remember that it's impossible to have true long-range orientational order in a two-dimensional system that's emerging from the breaking of a continuous symmetry. So-called Mermin-Wagner theorem. We'll see this in numbers or in graphs later, but so an example is the XY model. XY model are little magnets, if you want, spins, usually sitting at the nodes of a lattice in 2D. Okay, and they try to align with their neighbors. Okay, and that's in competition with the temperature. When the temperature is low enough, you have global order. All the little spins, magnets are more or less ordered globally. But that order is not perfect, cannot be perfect. Not only there are some sporadic activation of defects, pairs, which do not do much, in fact, but you also have, in fact, due to these fluctuations, spin wave fluctuations, you only have quasi-long range order, meaning correlations decay in space, but very slowly algebraically, but they do decay, so that in an infinite system, you cannot be ordered. That's the quasi-long range order for the impossibility of long range orientational order in equilibrium. Now, in 1995, which for some people, including me, marks somehow the birth of active matter physics, even though there were earlier works, of course. Vicsek, Tamas Vicsek, and collaborators, and John Toner and Uri too, directly argued that you can have indeed true long-range order in two-dimensional in, let's say, in active systems. If you think about the XY model, if you force the spins to move, now they're not fixed on the nodes of a lattice or something, but they are forced to move in the direction indicated by their spin or some direction correlated to that, then as we will see, you can indeed have true long-range order. So that out of equilibrium system, because you force the spin to move, is what breaks the conditions of Mermin-Wagner theorem, which is still valid, of course, but does not apply. Okay, this Vicsek model, as it's now called, and the Toner-2 theory, as some people call it, this is an emblematic example of what I call DADAM, dry, aligning, dilute, active matter. And I think I have something to explain this here, yes. So since 1995, as you know, many things have been done and still growing. Here is a very crude representation of a field of active matter. It's growing. You have to imagine this growing in more than 3 dimensions, of course. And you have here some main axes. For example, is the system wet or dry? So if active particles or active objects move, there's a surrounding fluid. If you can neglect the surrounding fluid, which is sometimes the case, you can have a model which ignores this, and it's called, that's dry active matter or dry models. If you have swimmers interacting only via hydrodynamic interactions, of course, that is a case where you cannot at all ignore the fluid surrounding the swimmers. Okay, that's wet, fully wet. In fact, in between, you have all kinds of intermediate situations. If you think of bacteria crawling on a substrate, they're inside a fluid, but they're on the substrate. So it's a mixed hybrid system in between wet and dry, where you cannot really fully model with a dry model. But on the other hand, it's not really just the hydrodynamic interactions that play.
Excuse me, sir.
Yes.
Sit here.
Yes.
Sir, my question is about dry and wet system.
Yes.
So in both case, hydrodynamics are present, right? But in one case, we can neglect that, and in other case, we cannot.
Yes.
So is it the definition?
That would be my definition.
Okay.
Yeah. I
But-
mean, you know, if people who are coming from fluid dynamics and consider only swimmers and only their far field interaction, then it's fully wet, then it's very clear, it's only hydrodynamics. But in fact, many micro swimmers, or even not so micro swimmers, they come in very close contact. Then you have to deal with a near field that becomes already out of the range of simple hydrodynamics. Bacteria crawling, when they crawl collectively, or they're in a fluid layer, this fluid layer is in contact, direct contact, it's very thin, and it's contact with some substrate. When they move collectively, or even when they try to move collectively by agitating flagella together, they cannot swim in the fluid because it's jammed, you know, there's just no space to swim. But because they collectively excite the fluid itself moves and displaces and rotates the bacteria. So that, and this is a system with lots of friction. So it's not, you know, simple 3D hydrodynamics. It's not dry because the fluid is what mediates the collective action that displaces the bacteria. But they're so dense that they touch each other and they align because they're elongated objects. So this is a very common case, actually studied by physicists also, in which you have all the characteristics of a dry aligning system like Vicsek or whatever, but you must put it inside a fluid to account for the right phenomena. So there are all kinds of examples, more or less wet if you want, or more or less dry. And so it's a continuum here. In fact, many systems are in between, as we now realize fully.
Thank you, sir.
Okay, so 3 axes, there are more. Dry, wet is key. This is a very rough one, which here it's, you know, I put alignment, repulsion, which are the 2 simplest interactions between particles that people have been thinking of. If you have only alignment, which will be the case today, it's a bit unrealistic if you want, because the alignment could come from contact between objects with a, you know, finite shape. If you have only repulsion, that's the case of this mobility-induced phase separation. The particles are usually considered axisymmetric. They just interact by more or less hard repulsion. This is another case that has been studied a lot, of course. And then whether your system is dense or dilute, of course, is going to change a lot of the physics. So here are the famous, you have heard of them because I saw some lectures about this, so-called active Ramanujan particles, which are persistent random walkers with a persistence time length, okay, and a finite size, and some kind of pairwise repulsion between them usually. That's what gives rise or may give rise to this motility-induced phase separation without attraction in the presence of repulsion. Okay, that's a case. So that's purely repulsion. This is purely dry, and you go from dilute to dense, and you have phase separation around here. What we're talking about today is that that's right here in this corner. So it's a singular case if you want. You have only alignment. It's strictly dry. Okay, that's why we're here. But what I usually say is that whatever happens in between, and in particular not too far from here, in this hypercube, you better understand what's going on in this singular case if you want to pretend model or understand what's inside. Now, the bacteria was mentioning that this certainly lives somewhere inside this cube. Okay. Oh, what did I say here? Yes. Okay. So our best understanding of all this hypercube is in this simple singular, if you want. It's not that there are no experimental configurations or systems that are really described fully by Dadam, so to speak. but very few, in fact. But it doesn't matter if it's few. What matters is that this is important to understand if you want to understand what's inside. And as I will say today, since 1995, that's, you know, almost 30 years ago, a lot of progress, a lot of surprises, and still some to come, and some points are not understood, as I will stress later. Okay. So it's not that everything is understood, and it's a closed lecture. There are still some pending important points. Okay, so, oh yeah, I could do this. All right, so as I said, for DADAM, dry aligning dilute active matter, or dilute aligning dry active matter, whatever. The quintessential model is the Vicsek model, but you could think of other models. I will briefly say a few words. In the Vicsek model, you just calculate here. So particles have a position, and they carry some angle. With angle, this is the angle of their velocity, and they move at constant speed. For all this is for simplicity, of course. And the main interaction, the only interaction, is that somehow the new direction of a particle is given by the average direction, just the ferromagnetic alignment, the sum of these little velocity vectors, if you want, in a neighborhood of size 1, also for simplicity. And that is in competition with some noise here. Okay? Now, this alignment, ferromagnetic alignment, could be a nematic alignment, which is in which, for example, you know, if you know what I'm saying, you know what I'm saying. If you don't know what I'm saying, let me put it in a cartoon. Nematic alignment, if the angle between the two incoming particles is acute, they will align, okay? If the angle between the two incoming particles is obtuse, they will anti-align, okay? That's nematic alignment in a nutshell. Of course, if you do this locally, you change the symmetry of the interaction and you change the symmetry of the global behavior emerging, okay? Now, a lot of what I say about DADAM is true also for nematic systems, and especially the next slide. Now, for the Vicsek model, here, this is not quite the original version of Vicsek, which is at the origin of a controversy with him in some sense. Here, what you do is that so you have your positions and angles at time t, and at time t plus dt, this is a discrete time version. You calculate the mean orientation over the neighbors, including yourself, okay, at distance 1. If there is nobody, it's just me and nobody else. If I have some guys, it's the equal weight weighting. All these simple things, equal weight weighting, constant speed, unit interaction range, isotropic interaction range, all these things are for simplicity. You can break them to some extent that will not change the behavior. So you calculate this local average direction. That's to tell you that you only consider the direction of the angle of this resulting vector here, okay? To which you add a random angle of some, root mean square eta here. So if this is very strong, that dominates the interaction, and you have basically persistent, more or less persistent, but not so persistent random walkers that align locally when they meet, but they quickly disalign. So at the next interaction, they have forgotten the previous alignment. So there's no global order emerging, no order at all. So that's the case when the noise is strong or the density is low, because if the density is low in between interactions, even if the noise is low, there's too much to go. When I'm alone, I'm still subjected to the noise. So I have a random walk, persistent random walk. If these interactions are too sparse because the density is too sparse, then I will not order. So basically, this is a snapshot, very interesting snapshot where you see a bunch of little arrows in random directions, okay? But if the density is larger or the noise is lower, and still not zero, in spite of fluctuations, all the particles, in a finite system at least, will take a mean global direction. See, the graphics is really degraded here via Zoom, but anyway, which is indicated with a big blue arrow, okay? So in 95, Vicsek did this. He said, we have this. So the idea was to think of the simplest possible model for collective motion, which is a very good idea. He said, well, we have this and we go to this, or we do it at constant density, changing the noise, strength, eta here. Okay, so at high noise, it's random walking. At low enough noise, I have this. In between, there is a transition, order-disorder transition, like in the XY model, except that the spins are moving over time, right? And because of thinking of this XY model thing, Vicsek focused on the transition, which he claimed to be a continuous phase transition. We'll see that's not true. Okay. Whereas Toner and Tu, as we will see later, they actually were interesting. They realized that this is a 2D system. This thing here is emerging from obviously breaking a continuous rotational symmetry. And could there be true long-range order? So, Vicsek actually did not think about it, at least not explicitly and not in the paper, if you read it. And the updating rule in the paper is slightly different from this because it involves 3 time steps, but it doesn't matter. Okay, so that's a discrete time version of lattice with angular noise. You can do things on lattice if you want. You can do things with different types of noise. Most of these changes will not change what I'm going to tell you now. And most of what you will see, there may be exceptions, but maybe I don't remember even myself, have been done with angular noise at least, sometimes continuous time. We will see this later. Okay, so now, coming back to sort of wider perspective, all these DADAM systems, so basically including the nematic ones and some mixtures of it and things like that. In all of them, the phase diagram in this global density, noise strength, basic parameter plane. In the Vicsek model, you have 3 independent parameters, so to speak. The noise strength or the coupling strength, if you have it, but they go 1 in 1. The global density and the speed of the particles. The speed of the particles doesn't do anything interesting in the Vicsek model, as far as I know. I mean, if you go to very strange limits, okay, it's not clear. If you go to very small limits, very small speed, in particular, it's delicate to study. But analytically and numerically, we have no evidence of anything interesting. So basically, 2 main parameters in Vicsek systems or in DADAM systems: the variance of a noise, like the temperature in equilibrium, and the global density, which, if you want, also sets the interaction range or things like that, okay? And the phase diagram always looks like this. There is, for high noise and low density, a gas, random walkers, basically. And at low enough noise and large enough density, ordered or quasi-ordered phase, in the sense that the velocities are aligned. Or if you have pneumatic systems in which the particles reverse their velocity at some rate, for example, this is also true. Then you have only a pneumatic order, but so you have a quasi-long-range ordered liquid. Now, why do I call this a liquid? Why do I call this a gas? It's because in between there is something else. It's not a direct transition from order to disorder, like Vicsek thought. But the right way of looking at it is in terms of a phase separation between a gas and an ordered liquid. So one key thing here is that liquid does not have the same symmetry as the gas. Contrary to it, in equilibrium, you would have a parabola here, okay? Something like this. And the critical point here, for those of you who have not forgotten this, okay? Now, because here is, in some sense, because the symmetry is different in the liquid than in the gas, the only way they can really be critical is at infinite density. And indeed, if you go to the limit of infinite density, the 2 lines here join again, and you have a continuous transition, but then no space anymore, no physical space. This is in 2D, in 3D, etc. now in between, you have coexistence between the liquid and the gas in a phase separation scenario, and that takes different aspects depending on the type of model or system you look at, and we'll see what it is for Vicsek model, but it's true for all the other cases too. Okay, so yes. Where is the mic? Here's the mic.
So in the liquid, why do you call it quasi-ordered liquid, even though like they have liquid have like long range correlation? Like, why is it quasi? Like, I don't understand that.
Why is it?
Quasi-ordered liquid.
Yes, in the nematic case, we know that at least in this dry context, asymptotically the order is quasi-long range, just like in equilibrium, you would say. But it has other features which are clearly non-equilibrium. In fact, you can have a very, very long range of scales over which you observe true long-range nematic order. And beyond this crossover scale, we should turn to quasi-long-range order. But I will not show this today. But basically, it's just at this level. It's not that it's an equilibrium. It comes down back to equilibrium, so to speak, which could happen. But from the viewpoint of a global order, in the nematic case, asymptotically, it is only quasi-long range with algebraically decaying. Okay, so in between, this takes different. So now for the Vicsek model, okay, again, you have a gas, the liquid. In between, you have something like this. This is the same size system, different density, I think, in between the three. So this image of a coexistence phase here, this snapshot, is in between this and this, increasing density, if I'm correct. So what happened here in this relatively small system, and what Vicsek missed in '95 is that this is I don't remember, this is probably at the limit of the systems he was looking at in '95, 200 by 200 density 1 or something like this. Particles, not all the particles are shown here. You have a few only for your edification. So here, spontaneously, the particles have arranged themselves into this dense object in which they are aligned according to the magenta line. And this thing moves, of course, okay, recruiting the particles in front and leaving behind, well, a statistically equivalent number of particles, and it's a steady state like this. So in a small-ish system, you would see one of these objects. In a larger system, you will see something like this. This is a movie, if it works. You will see. So now you don't see a real movie. These are snapshots which are separated by 10,000 time steps, maybe. But you see that after a short, and these are millions of time steps, and these are millions of particles inside, and you only see a coarse-grained density field here. Okay, you see that spontaneously you've had 1, 2, 3, 4, 5, 7 such bands which have formed. I mean, arrange themselves. If I play it again, you can see that they really want to arrange in a regular smectic pattern. For those of you who know what is a smectic, this is a smectic. You see here, you see the elastic modes between them. I mean, because the movie is not running very smoothly via Zoom, I'm sorry for this, but you can see that they're really elastically arranged so that to finish at this steady state in this system of 7 perfectly aligned bands, etc. But you see there are lots of fluctuations. They must be interacting with each other. See, this one has lost this packet here. This packet will be recruited by this one, probably disturbing this one, and then something and so on. So this is one of the things we do not understand, but I will mention this later. Okay, now the key point, it may be this graph. Here we have, well, some measure of global polar order. So Vicsek model is polar order. You can measure the global velocity normalized by a number of particles and the individual speed. That gives you take the modulus of this vector, which is between 0 and 1, and this quantity is represented here. So you are near 1, meaning you're very ordered, okay? And what you see here is in systems with periodic boundary conditions, as a function of a system size, of a linear system size in big squares, if you want, in 2D, you see how this thing behaves. So it decreases with system size. So this is log, and this is also log, although you don't see it because it's very compressed near 1. It decreases with system size, but slower than a power law, because if it were a power law, that would be a straight line, all right? Okay, and a good fit of these numbers, of these data here, is that it goes like a power law to some asymptotic value, which is of the order of 0.8 something here. Okay, so there is an well-defined true long-range order asymptotically, as far as I extrapolate this numerical data, but this data is very clean, you know. And the way we go to this infinite finite non-zero value pi infinity is with a power law, like a power law. So the difference between the asymptotic value and the true value as a function of L is a power law with a slope of the order of 2/3, minus 2/3, okay? And what I don't show you here is that indeed, if you measure correlation functions for the fluctuations of density or of order, these fluctuations decay algebraically in space and time, like they would for any system almost, I mean, density of it, where you break a continuous symmetry, like in the XY model. But here you have true long-range order. We'll see this a little bit better with the 102 business. Yes.
So like in the last
Previous slide?
No, this here only in the last, when these, like the layers are moving basically.
Yes.
Of particles. So on what does it depend that which particles will be left behind and others move in front, and the particles who are left behind, they merge with the like preceding layer?
So actually, we don't know this very well. It's an interesting point, and for sure, a particle sitting here, for example, let's take this case with just one band, and the same band is coming back, so to speak. So if I am this particle here, I'm going to be joining the band very soon because this moves, you know, at finite speed. The speed is actually not too far typically from the nominal speed of particles. And once I'm in the band, I will stay in the band for a pretty long time. And I don't know of serious measurements of this, actually. How long do I stay in a typical band? Probably depends on parameters, you know, but certainly in a small system like this with a band, you know, if you have, you can also have a single band. So what happens, you know, in the phase diagram, which I can draw it here because it could be useful later anywhere. You have basically the phase diagram with the density here, rho 0, and the noise strength data so far. Sometimes I change the notation, sorry. If you are here, near here, you will see a small fraction of liquid in the phase separation language, meaning not so many bands. And you can indeed have, even in a arbitrarily large system, you can only have one band if you carefully tune your parameters, okay? This single band is not interacting with anything because there's lots of gas around. So it would be interesting in this limit at least to study how long a particle stays in the band, but I don't know. Certainly for a long time compared to the band width of the travel, the time it takes for the band to travel over its width, but I don't know. Yeah. Yes?
Here I can see that all these bands are traveling in the same way. Can it happen that some of them are moving in some direction and some?
Next slide, coming soon.
Okay.
Another one.
infinity?
How do you get, yes, very good question. You know, we have reasons to believe there is true long-range order. If you try fitting parallel to zero, that does not work at all. I mean, you know, parallel to zero would be a straight line, so there's no way. If you try other fitting functions, you can try away. But we have reasons because of Toner and two and more general reasons to believe that if there is true long-range order, then you go to some finite value like a parallel. So if you try that sort of scaling, that works. Also, you can do directly, if you measure here the local slope, the data is clean enough. You can imagine more points even here because this one is a little bit expensive, but not so expensive. This is rather easy to measure actually these days, you know. And so the data is clean enough here because it has been run for a long time and we know very precise values. But you can measure the local slope of this log-log plot. This is the local exponent, so to speak. And you see that this is a straight line. I mean, with your eye, you know, okay. Actually, I have I do have, in the second part of the lecture, we do it on a much more difficult case. And we see, the question is whether this is really a parallel, whether, well, not this one, but with Quenched disorder. But anyway, if you take this data, add more points if you want, measure the local slope, say between 2 points in the log-log scales, I measure the slope. So this is the local exponent. This thing will actually be this thing will be a constant here, or will decay linearly with L if I don't subtract the pi infinity. So there are clear evidence. This can be obtained by just a fit, and you say other fits would do it just as well, true. But then if you go a little bit deeper and you look at the derivative of this, then you see very, very clearly that it is an algebraic decay, okay? These are technicalities, but very important ones as soon as you manipulate logs, you know. Here, nowadays, we can do much larger systems, but you will see. So this is, by the way, this is only for the liquid phase here, right? Now, the coexistence phase, as I told you, it's coexistence in the sense of phase separation. And one good evidence of this is, for example, in this picture here, this is a system, two different systems, same system size, different global densities, okay, same noise. So the only thing that has changed, but here I have, let me guess, 3 times the density in the green system, which has 6 bands, is 3 times the density in the red system, which has only 2 bands, roughly, you know. Of course, there are quantization problems, but basically, the key thing is that the gas level is really the same. You can see it here. This is the same thing here, where we have time averaged in the moving frame, the profile of these bands, the green bands and the red bands, and you see that and the gas level, and you see that these things are on top of each other. Okay? So the fact that varying the global density, you have these objects, dense objects, in a gas which has a very well-defined density, vapor density, that's for me a good working definition of phase separation. Okay? Now you see not only that, but as I vary the global density, if the quantization problems are taken care of, this is exactly the same profile that we see. So you have the quantization of a liquid in terms of these well-defined objects, you know, so much that if I have my global density and I know the gas level, I know how many particles I have to fit in the rest, in the liquid. I know that this liquid must be made of objects which are transversally speaking like this. So I can calculate a priori the length, the total length of bands that I need to see in my system, appear in my system. And that's true, that works. So, you know, I know the gas, if I know my system size and my global density, the gas level, then I know exactly how many particles I have to put in the rest, in the liquid, in the bands, the moving bands. Because I also know the profile at parameter, at fixed noise value, N over profile, and I can calculate it numerically. Then I know exactly, more or less exactly, what's the length of bands that I have to put in my system. And indeed, if you simulate large systems, as I will show next, you can find many different configurations of bands. But if you calculate the total length of these objects, more or less what I say is true, or in finite systems is always not strictly true, but very nicely true. So here are other manifestations of this. Here, if you vary the length of your system as a function of the length along the propagation of direction of propagation in these smectic, these are smectic arrangements. You see a number of bands goes linearly with the system size, okay? You see that here as a function of, well, that's the same thing. Here it's actually as a function of rho zero also, as a function of density. The higher the global density, the more bands I have, and this is linear with global density. All these simple things that you would expect in microphase separations. Microphase separations meaning there is a typical size for the dense objects that form, and the sum of them is a liquid fraction. This liquid fraction goes linearly as you would expect in macroscopic usual phase separation, but here it's quantized by these objects, and they are moving also in space. Now, so far, we have only seen smectic, nice periodic arrangement of bands, okay? By the way, it takes a long time in the computer for the bands to arrange in a smectic configuration, especially if you don't have too many. If you have a very large system, you're very near the binodal there, you say you have 2 or 3 bands in a very large system, it will take forever for them to keep more or less equal spacing or reach equal spacing.
Sir?
Yes.
Can you go to the previous slide, please?
Yes, I can.
Actually, in figure C and D,
Yes.
I think I missed something. Could you please explain it?
So here, sorry, myself, it's been a long time I've looked at this myself. So here you have 2 noise levels and data as a function of the length of the system along the order X, okay, at fixed global density. So, you know, the density is the same. So if I increase Lx, I increase the number of particles, of course. And I put a number of bands, I observe a number of bands in there, which is growing linearly. The slope depends on the noise level because the shape of these objects also depends on the noise level. The shape of this thing only depends on the noise level, not on the global density. Okay. And here, it is, in fact, at fixed. I think the data, it may be at 2 different transverse. This is L parallel, must be Ly, so must be the transverse size. Anyway, the data is obtained as a varying the density here, mostly. So vary the density. At the beginning, I have 1 band, then I have 2, then I have 3, 4, 5, and that number of bands goes linearly with the global density. This is just to show that I can collapse things at different transverse dimensions if I subtract the gas level, etc. Roughly this.
Okay. So, so is it like by varying the density, we'll get more band than by varying the noise term?
Or varying the noise, basically you change the shape of these things.
Okay.
And you see that here at lower noise than in blue than in red, you fit more bands, meaning they are smaller in this case, etc.
Okay, thank you.
Now, next slide shows you that you can have, in fact, all kinds of, these are steady states, okay, in smallish systems also. Here now it's 1,000 by 1,000, okay. You can find steady states like this in which 2 systems of band. This is actually 1 band only because it's wrapping over itself, but this is 2 bands and another one here. You know, these coexist. Same system, same density, same noise. To the point that you can engineer configuration you need or you want. You know. Okay, some surprises. if you look carefully here, these two light blue, so the color is the orientation of the particles inside, coarse-grained. Okay, so this is going at 180 degrees. So it's going to the left, these two, and these are going, you know, whatever, up, I guess, or down, down. If you have a good eye, you can see which edge is denser, which is always the front edge. Okay, so here the two two light blue bands are at this distance. They have chosen to be at this distance from each other and not equidistant in X. And I think I have another. Yeah, so this is something we don't quite understand. That's why I'm showing it to you. So here you have this at some time, okay? Or maybe this was actually a copy. Oh yeah, you can see here that this, if you divide this in two, these are two copies of the same system. The guy who did this, he found a system with 3 bands and this, and then duplicated it. After 10,000 time steps, it seems to stay more or less like it was. After 1 million something time steps, the 6 bands are still here, but they have chosen to be in a symmetric arrangement, but not covering all space. So this is due to the interaction with these other bands, of course, which are complicated, etc. And these are, you know, but basic, yes.
So what's happening at the overlapping region, like near the boundaries?
Yeah.
Don't those particles see the other band's velocities?
So that's where the question of before would be interesting. Now, what does a particle do? Does it jump from one band to another? What we know is that these objects are very dense, typically. Even here, it doesn't show so much, but they're typically dense, and they introduce perturbations along the band, density perturbations, and also order perturbations, of course, along the band. Order and density strictly coupled here in these systems. And so this is complicated. I don't know the answer, but certainly this is where to look for an answer if you want to understand how these things interact. But all right, so just to show you, now I have a
Question.
yes.
I'm kind of confused by the fact that these two bands are not merging and forming one particular band going in one direction, because in the original Vicsek model, that's what used to happen, right? The aligning interaction would make them go in a given direction, but why aren't they doing that?
These, you mean that why are they not?
Why there are two bands?
We don't really know. I mean, we in continuous descriptions in Tono 2, or slightly better than Tono 2 simple equations, which you will see next, we also see this. So these, we understand the single band propagating. We understand there are many different types of them. We can check their linear stability of each band, but solutions with 2 bands crossing, we see them. And as you can imagine, even in a PDE, which, you know, okay, it's not particle model, it's not so obvious to understand. But it's there too, yeah. It's very robust, resists very strong fluctuations, in fact, happening at the intersections. Also, bands can pass through each other, bounce on each other. Not so, I mean, depends on parameters, but sometimes they can do this for a long time. Or on a wall, they bounce on a wall, come back. So these are very robust, nonlinear localized structures. And as you saw in the, oh, you didn't see the real phase diagram. The real phase diagram is actually the coexistence region is even larger than what I drew here. It's a bit, you know, it's actually not negligible at all. You know, some people say, oh, you have this marginal instability near the onset of order. No, it covers a very large part of parameter space, in fact. Another exotic
question.
Yes.
Sorry to interrupt. So you mentioned that the configuration B is stable. Do you quantify that at the level of linear stability, for example?
No. Even linear stability of one band in the PDE We are working on this, but as you know, a localized object, linear stability, there is no very good way of doing this. You can do it numerically.
That's what I was thinking, numerically linear stability
So
and what
numerically, we didn't do it, but numerically what we can do in a PDE is that we generate a solution, and I show you how we can do this. We put this in a PDE simulation with some noise. How much noise, but some small noise, and this thing resists a bit of noise. So it's linearly stable for all practical purposes, but we did not calculate the stability. Many of the solutions we have are linearly stable. Now, two bands crossing, because we observe this numerically, I'm pretty sure they are linearly stable, but to study this properly is very hard. Yes.
So I have a very naive question.
Go ahead, shoot.
When these bands propagate, does they satisfy any wave equation or not?
Satisfy?
Any wave equation?
No, in the sense that, as I showed you, that they like the symplectic wave-like arrangements, and this corresponds to periodic orbits in some dynamical system viewpoint of it, which I may arrive at. But sometimes they don't, and look at this, for example. This is a system of bands going this way here, and another one going this way here with different periodicities. And this thing is stable, at least in this geometry, it is stable. Okay. And so that, it is not a wave. It doesn't have a structure, analytical structures of waves, but it has analytical structures of a train of politons or periodic pattern in a dissipative PDE. That's what it is. So here, again, and now we're going to large systems, as you can see. This, we believe, is stable, at least in this geometry. So these lanes of bands, so this one going up, this one going down, up, down, up, down, up, down. These started from something which was, again, very different from this. The minority up phase, so to speak, here chose to be finally into 1, 2, 3, 4 objects of precise width, leaving this in the middle. And we also see this in some continuous simulations, but it's difficult to see. The good news about this is that if you make this system now much longer, if you increase Ly, then these interfaces here are unstable, in fact. Asymptotically, you don't have to worry about these things, but they show up in finite systems rather spontaneously. So, all these zoo that you can make with bands and various systems. And in finite, even large systems like this, they are stable. Okay. Yes.
So when you go for large simulation boxes, here you are taking LX, LY are pretty large, very large system sizes, and you are simulating it for a really long time. Yeah. So it becomes computationally very challenging to do that, right? After certain length and
the code, is always the same. The code is super simple. It's optimized, of course, but simple tricks. And it's just a matter of having a big computer. Here you have whatever 10,000, 25 million particles run for 100 million time steps. In fact, this may not even be time steps because this may be a continuous time version. So maybe you add another. So this is huge. But these days, if you're in China or in Germany, warm up the planet a bit. So the code is super simple. This is done on a parallel machine, of course, but that's also super simple to do. So really, with one day of learning MPI or whatever, you can do this. Easy. It's just a matter of how big is your computer and how patient you are. But to answer such questions, we do need large systems and larger systems as far as we ask ourselves further questions, and you'll see, I think, next slide. No, not quite. Next slide is a complicated slide. Maybe I go fast here. This is to convince you that these, in the band phase, at least for the SMECTIC configurations, there is true long-range order also. Okay, so you say, here it's long-range order, as I showed with this log-log plot before, and here, at least for the SMECTIC arrangement of bands, as a function of the length of the system, the global density converges to a well-defined value. You can understand this by, there is a preferred spacing between these bands also at fixed parameters. Not only the profile is well-defined, but the spacing between the bands is also well-defined. There's a preferred asymptotic spacing. And then at finite size, it never matches exactly. So you have a residual length. And this is labeled with colors depending on the residual length, having guessed the true asymptotic wavelength. So basically, the message here, if you think a little bit, even in finite size systems with this SMECTIC arrangement of bands, you can see, you can convince yourself or show that there is a well-defined spacing, ideal spacing, asymptotic one, and work out the finite size scaling due to the incommensurability of system size with the spacing, so that you can use it to infer the asymptotic spacing and all that. So all this is a bit complicated, can be done if you're interested, because we have too many questions I will never get to the end of the talk. So I speed up this. The message here, the coexistence phase here also has true long-range order, okay? SMECTIC order for SMECTIC configurations, meaning how regular is the spacing of the bands. We also believe it's there, but we're not sure, because one big problem is this. So far, I've shown you systems which tend to have rather short bands and the travel in a long system, you know, all of these SMECTIC things, etc. What about the stability of one or several super long bands? Okay, so that we don't know. We're still working on this, both at continuous level and at microscopic level. I wanted to show you this because this is data we have had a few years ago, but now we're working more seriously on this. So you take the band as a fluctuating interface. This is one band in a smallish system, maybe 1,000 by 200 here. At the time we were doing such things, now we do, you know. And you have ways more or less rigorous to define where is the leading edge. Okay, you take this as a fluctuating interface. And you ask yourself, how is this thing? Is this thing roughening, you know, in the sense of KPZ? Or KPZ would be the default thing you can think of because it's moving, it's asymmetric, etc. If you know KPZ, fine. If you don't know KPZ, just bear with us for a few minutes. So this, you see here that if you look at the width square of this interface as a function of time, for KPZ, you would expect the slope 2/3. Here you see 1/2, which is more or less like what you would expect for so-called Edwards-Wilkinson roughening. Okay, so it roughens a bit, but then here it's not very clear actually, or fairly large systems. And here you look at the width, asymptotic value of the width as a function of system size or transverse system size here. And you see that after some transient here, which is beyond 1,000, you get maybe a slope 1/2, which is not KPZ, not anything we know. I'm not sure at all about this data. This data probably shows that it's complicated and it's smoother than KPZ, and we don't understand. So we're working on this now, but this is a totally open problem. So before, you know, the stability of a SMECTIC with fluctuations, we better understand the stability of one isolated band. One problem here is that the band is not isolated. You know, the system is not long enough in this direction so that the band forgets about what it has left behind. What the band leaves behind is immediately revisited. Okay, so is important because we don't know if it turned out, even at the deterministic PDE level, that a single band has a long wavelength linear instability, which we never saw because it could be very long wavelength. And what I just said about long-range order here would not be true, okay? And what would it be? We have no, so we don't really know. Okay. So I say that if you are here, you see first one band in a whatever your system, one band. If it's large enough, it will be one band. This band has a finite width, so it could be a very, very lonely band in a very, very large system here. If you are near the other line here, so far the other line has been always not so well defined, to be honest. And these are simulations that show you finally what happens. So here we are, again, sort of these very large systems. And you see that what you see is some mess of bands, okay, crossing each other. And in between, a region of toner 2 liquid. This region, if you get closer, closer, closer to the binodal here, gets bigger, 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 and finally you only have a liquid. So you really also have phase coexistence. It's slightly different from what everybody imagined before. This is the first time we show this data. So, but indeed, this is a profile which shows you that you know, if you get, again, it goes linearly with, if you go at fixed density here, approaching horizontally, so to speak, this object gets wider and wider linearly with global density until 1, covering 1, covering the whole surface, so to speak. Okay. So this is what happens near the liquid binodal here lying. Okay. And to see this, you need these system sizes. Otherwise, you never know what you're looking at. Okay, toner 2 theory. So in 95, back in 95, John Toner and Hugues, two listening to Vicsek giving a seminar on his model, immediately thought that, is it that, because Vicsek was not even realizing, he assuming, or whatever it is, anyway, wasn't clear. So they were perturbed and they say, could it be that there is true long-range order? Because their first reflex is, there's no order anyway, so what are you talking about? But anyway, so then they wrote down this so-called hydrodynamic description. So in terms of density, it's a compressible fluid. Density is advected by velocity. Velocity equation here is more or less Navier-Stokes. You know, you have Navier-Stokes nonlinearity with some arbitrary coefficient. You have Navier-Stokes-like terms that do not play much role, maybe, but are possible by symmetries. You have viscosity. Where is viscosity? Here. Anisotropic viscosity, anisotropic pressure. Okay. And this part here, which is supposedly a Ginzburg lambda part, or you know, which gives the velocity field when alpha is positive, some basic value. V squared is of the order of, you know, alpha over beta, which is the active forcing. So it's you want to marry Navier-Stokes and Ginzburg lambda in a system which has less symmetries than Navier-Stokes, obviously, or less conservation laws. And the simplest terms that you can write that's, you know, satisfy all constraints are like this, plus some ad hoc noise. Okay, so that is what they wrote down. And they then did some RG calculation focusing on the question of whether the ordered phase, the liquid phase, can really be stable, meaning is there really true long-range order, or are fluctuations also destroying this? Okay, so that was 95. Yeah, so basically they have some framework to predict anisotropic scaling of correlation functions of, let's say, the transverse velocity here. We could argue whether this is a good quantity or not. As a function of, it's a 2-point correlation functions, 2 points separated by some vector r. The scaling is the power law of r It depends on the longitudinal and transverse position of the 2 points you're considering, so that along the longitudinal direction, you have one scaling exponent, along the transverse direction compared to order, some other scaling exponents. All this framework is quite natural. Okay, this is not the result of RG, but this is the right framework to look at this RG problem and other problems. Okay, and similar relationships for density correlations, also for two-time correlations. So basically, we have predictions that the correlation functions of fluctuations should scale with distance and time with some specific powers related to each other. And this is anisotropic scaling, the way the correlations decay along the direction of motion, and transverse to the direction of motions is with different exponents. Okay. Now, what they did find is that below dimension 4, the linear theory breaks down, so renormalization is important, and you have to work out the effect of fluctuations. They did find this anisotropic, they predict this anisotropic long-range correlations, anisotropic scaling meaning, and they concluded to true long-range order, even in 2D. This is the predictions in 95 for the various exponents that I don't want to define more precisely here, okay? Then what happened is that they realized, John Toner realized that the calculation of 95, in which they were spared to calculate diagrams, etc., because they were using some extra symmetry in 2D, was not true. I mean, the extra symmetry does not hold if you consider the full problem, and they did not consider the full problem. So then there was no more exact results. So then we decided to look numerically seriously at what happens. And this is what we measured on 2D simulations of Vicsek, okay? You see that differences are very large in exponents, depending on which one you look at, of course. But this one, this is the anisotropic exponent. This is the difference, or one would be isotropic scaling. So actually, transversely and longitudinally would be the same scaling exponents for fluctuations. In fact, we find something which I cannot square is not 1 in 2D. In 3D, it's indistinguishable from 1. So this is very, very different from this. And this was one key point of a theory, or this is one key point of a theory, that the scaling has to be anisotropic. It's not sure it's true. Anyway, right now, we do not have any RG calculation of exponents, except this 95 thing, which relies on some symmetry which does not exist. And we have these numerical facts. So even that is, and there are other deeper problems I don't want to mention here. So basically, we don't know that much. The qualitative framework works. I mean, you can see that the various scaling and range predicted by Toner and 2 actually work. Actually, the sound modes, which is something at linear level, also is true, and so on. This has been observed even. But at non-linear level, at fluctuating level, nothing is so certain. And these being numerics, you know, even though again on large systems, etc., this is always be handled with caution. In 3D, even more difficult, of course. And you see here. Okay, so anyway. Maybe I skip this for now. I'm not sure how am I doing in time at all. Okay. The previous slide, I come back to it, but later, it doesn't matter. So just here a few words about, in fact, what me and people around me have done is insist that we should always go from microscopic models, Vicsek or whatever, to the continuous theories, not just by writing terms allowed by symmetry, but by deriving continuous symmetry theory from the microscopic starting point. Okay, so there are various ways of doing this. The main advantage, if you look at Toner 2 equation, you know, it's a bit cheating, but let's, for the demonstration, Okay, so here we are. This is a compressible fluid. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 functions of a density in principle. Okay, so with that sort of a parameter space, man, you can do all kinds of things. Are you allowed to do them? Depending on what you're thinking of. Not clear. Okay, so if you derive from a microscopic starting point and you pretend that your end result, your continuous theory, is faithful to the microscopic starting point, then you can really check. You have your end result with the coefficients now depending explicitly on the microscopic parameters level, and you can check. That's honest way of working. Okay? Of course, it's a bit harder to do, and you cannot cheat so much. Of course, the assumptions that you do to derive the continuous theories are often very bad. So that's where, you know, as I was starting to write in this slide here. So there are methods to do this, okay? Most of them. They first write a kinetic equation for the density, the one-body probability. So the probability F here, the probability of finding a particle at position R with angular direction theta at time t. Okay, to write an equation for F and just F, you need to factorize probabilities for the two-body function or the n-body function, depending on what you do. And typically what you do is factorize, okay? So factorizing is a so-called molecular chaos hypothesis in Boltzmann kinetic theory thing, okay? Which means that in between collisions, you lose memory. And so you can factorize probabilities legitimately, okay? Now, if your collisions interactions are alignment, two particles come, they collide, they align, then they stay together for some time. So that's very, very bad for molecular chaos. And indeed, if you look at how justified it is quantitatively to assume factorization of a two-body probability function, for example, this is really not true. Okay. Nevertheless, if you want to arrive at what is in some sense a starting point, a kinetic equation just for the one-body probability, you need to factorize probabilities. So you need to do something very bad in the context of aligning systems. But you need to get somewhere. So you do this. Once you do this, you lose totally any hope of quantitative agreement by these methods. The best thing you can hope for is a qualitative agreement. So if I vary the microscopic level parameters, that I reconstruct my phase diagram, you know, I vary rho zero, I vary the noise strength, that tunes all the parameters of my transport coefficients of my PDE. I look at my PDE numerically, whatever. Do I find this, you know, with a gas, a coexistence phase with bands, an ordered liquid here or not, or do I find something else qualitatively different? I forget about qualitative agreement, numbers here and here, okay? But the shape, the general organization of a diagram, the various phases and the way they, you know, if I get this qualitative agreement, I'm quite happy. And so you do molecular chaos, you factorize probabilities, you have a kinetic equation for this. You can write it in terms of the angular Fourier modes of theta. So that transforms the kinetic equation into a hierarchy of PDEs, infinite hierarchy of PDEs for the various modes. So mode 0 is density, mode 1 is polar order, mode 2 is nematic order, mode 3, etc. So you have this infinite set of PDEs instead of a kinetic equation. Well, this is a kinetic equation. Then you need to truncate it or close it, truncate and close more or less cleverly. Okay. You can do it abruptly, you can do it not so abruptly, whatever. At the end, you hope to be, in general, you hope to keep only the important modes, so density because it's a conserved field and very important, and polar order because this is all about polar order, okay? And then you hope to factorize the nematic order, nematic field into basically polar field squared or something like this. And then you arrive at something that indeed looks like a Toner 2 equation, okay? In fact, in these simple systems, it works. In practice, not just from Vicsek-like things, but for many, many other cases, using a Boltzmann approach in which you assume that your system is sparse enough so that you only have binary collisions, which is not such a bad approximation, in fact. And you do Ginzburg-Landau scaling ansatz, which I don't have time to. This gives very good results, qualitatively good results. And this is, for example, the result. So if you start from a Vicsek thing in continuous time, and you do Boltzmann, so you say, okay, I only consider binary collisions. And I use a Ginzburg-Landau style scaling ansatz near onset of order. I have no size on the technicalities of this, but of course I could answer some questions later, not now. You arrive at something like this. So here, this is now a momentum field. This is rho v, if you want, is W. So you have conservation, of course, that's exact. And you have the Toner 2-like thing, which indeed has the Navier-Stokes nonlinearity here, the Ginzburg-Landau terms here. The viscosity is isotropic in this case. The pressure is super simple, also isotropic. And these other term with 1 grad and 2 Ws. So this is more or less Toner 2, a bit simpler because the starting point is simple. The good news is that we know lambda, mu, psi, nu, kappa as a function of eta, rho 0, etc., V0, and so on, the microscopic level parameters. Okay, now, if you study these PDEs now and you reconstruct the rho 0 eta phase diagram, you do find this. You do find the right things in the sense of you have 4 lines now here. 1, 2, 3, 4. Okay. From linear stability analysis, you have a 2 dashed lines. This one here is the loss of linear stability of a disordered homogeneous solution. Everything is 0. W equals 0 everywhere. That one is stable here, becomes unstable here. So that's the onset of order. It's replaced by the ordered solution W equals W squared equals mu over psi, okay, which is also a homogeneous ordered solution. In fact, this homogeneous ordered solution exists from this line down, below this dashed line here. It exists, but it is linearly unstable. So the homogeneous ordered solution is linearly unstable below this line, okay? And it becomes only stable below that second dashed line here. All this you can get from linear stability analysis of a full problem of a PDEs, which is not so hard to do, okay? Now the 2 solid lines here are the lines that are not so easily found. So here, in between the 2 dashed lines, you have no homogeneous solutions. You only have band-like things, etc., and you see them. And in fact, these solutions exist and are stable, observable until this dashed line here, and until the solid line here, and until that one here. So in fact, the lines that you would observe in an experiment are these binodal lines here, the solid lines here. And the lines you can get via linear stability analysis are the so-called spinodal lines in the phase separation language. So you recover the right structure, qualitatively speaking, with lots of information, etc. That's where we are satisfied. We have qualitative agreement, we understand better, and we can even study the band solutions a little bit more. Yeah. Interesting. There's a delay between this and this, about 2 seconds. So if you take now, if you think of, I want to find solutions which are homogeneous in Y, in the transverse direction, and only depend in X. and also travel are stationary in a traveling frame at velocity c. So this is the PD is now reduced to a scalar field M and along one dimension X, okay? I look for solutions that depend only on Z equals X minus CT. I don't know C, but okay. And then the PDEs become some ODEs. Okay, that's the classic stuff. The first one can be solved. You inject in the second one, then you're left with a second order ODE, a dynamical system with 2 degrees of freedom, not too hard to study. Okay. You can study this using so-called Newton mapping or other methods systematically. And you do find all kinds of solutions, periodic orbits, which correspond to these trains of bands, if you want, of symplectic bands. You find that's a 2-parameter family, depending on, say, the speed and the spacing between the bands, meaning the period of the orbit. You have a 1-parameter family of solitary bands. So here is just the speed, can be parameterizing this, for example. And you have a single heteroclinic connection between one fixed point and another. This can be arbitrarily wide. Okay. All these things coexist. So these are solutions of the ODE, which you get by shooting methods and various other arguments numerically. This means that these are solutions, they exist as solutions of a PDE, okay? Which does not mean they are stable in the PDE. Okay? So in the PDE, what you can do, as I said before, well, you just take this, put it in a PDE as an initial condition, put a bit of noise, whatever, and see whether it stays or breaks down. And when you do this, you find that many of the solutions, not all of them, but many actually not only exist, but are stable. This is a case here where the heteroclinic single domain, single moving domain is linearly stable. And that band thing is also linearly stable as far, and also many, many other band solutions are linearly stable. So at PDE level, deterministic so-called mean field level, you have infinitely many coexisting linearly stable solutions, which is not what you see in numerics of a particle model, the Vicsek model. Okay. I thought, yes.
So when you say ODE, you're basically looking at the system at the steady state? So you're taking...
Yes, you're looking for solutions which are stationary in a moving frame.
Okay.
You put yourself in a moving frame, Z equals X minus CT. You don't know C, but C is a parameter now. Your PDE becomes an ODE. You study this ODE with classic methods.
Sure.
You do all the counting of solutions. So you know existence of PDE solutions. You don't know stability of these PDE solutions. To do this is difficult, so we just do it numerically roughly. You put it in a PDE. You take your ODE generated solutions, put it in a PDE, add a bit of noise. Does it resist or not? And for example, this is a case where generically at all parameter values, you always have infinitely many solutions, not all of them, not all we found, but a fraction of them is linearly stable, including this one, always. Whereas numerically, as I told you, numerically, we only see one band and one spacing between bands, so meaning we only have one solution selected in the particle model, okay? So here, the Turner 2 deterministic level is not enough. And we don't understand this very well. What we can do, and we did here you have some of these solutions. How is it? Yeah. Here we started from this solution here, okay? And added noise, added scalar noise. This is because we were thinking about so-called activizing models. So forget about this one, but doesn't matter. This is the Vicsek, the Turner 2-like equation now. We add to the PDE derived, the Turner 2 PDE we had, to this. We add a bit of noise here, just like Turner and 2 did actually. Don't ask me what type of noise, but here we just did simple additive noise, but it doesn't matter. Well, I did two types of noise actually, doesn't matter. Now what you see here, if you start from this, put some noise after 400, whatever, you see fluctuations which are pretty strong in there, which is also a sign that you have strong fluctuations of density and order inside the liquid. But then after a long time, you're down, it breaks down to whatever 10 or whatever 12 bands here, okay? If you were to start with more bands than this, you would see the number of bands reduced to 12. So really, as soon as you put noise on the PDE, you select one and only one of these infinitely many coexisting linearly stable solutions. And that we do not understand. So this is very fundamental, as you understand, because obviously you have too many solutions, and then how do fluctuations select one? It's not clear.
Question?
Yes.
So, I mean, just at a very high level, so if you numerically linearize 3n equations, I'm wondering how much of, because you have n is of the order of 10,000 and so on, how much of these eigenvalues are, you can determine that it's negative, and how much of them are
we don't
not very
do,
clear?
I told you, we don't do linear stability of a band solutions. We just do, we put them in a PDE code with a bit of noise, and we see that this is a stable solution of the code. We can play with resolution. We can play with the amount of noise you put in. This is a Pullman's linear stability. True linear stability of a inhomogeneous solution like this, even though it's 1D, there's no good way of doing this, as you seem to know. So when I say these things are linearly stable, because they are stable in the computer when we add a bit of noise, at least on the initial condition, and we see that this thing relaxes. That's what I mean. Yes. Stochastic, yeah, SPD, sorry. Yeah. But basically, this is one of the important pending points. Okay, so we said, pretty good. Yeah, so far, I showed you that we if you take a Vicsek-like thing or any damn simple things like this, you can arrive at more or less the same level of understanding. At microscopic level, we have this ordered, the quasi-ordered phase, this coexistence phase. We derive PDEs, we study the PDEs, we can even have more or less analytical solutions for the inhomogeneous solutions observed in the coexistence phase. Still, there are important problems, like this one. How is it that we select one solution at continuous level? Are the bands really stable? Is the smectic order long range or not? Or do the bands roughen and touch each other in very, very large systems, et cetera, et cetera? Okay, there are important missing points. And the rest of the talk will be about all these things I showed you. If you start perturbing the Vicsek model in some meaningful way, not changing the speed or something innocent like this, how robust is all this, okay? And the answer is, you don't want to come back after coffee, is not much is stable, okay? All right, so we stop for half an hour and have further questions. It's good, there are many questions.
So are these bands seen in experiments, or it's only simulations till now?
Yeah, very good question. Is there any system that is a Vicsek system? My short answer is no. Now, some people claim to see Vicsek bands. They certainly see bands, whether these things are bands. For example, if you, because we are going to talk about this a bit later, the so-called Quenched rollers. So these are colloidal particles in a fluid, and they are in a weakly conducting fluid, and there's a vertical electric field, DC field, okay? It's well known that if a field is strong enough, the particle will start rotating on itself. If a particle is too heavy and falls on rests on the bottom of the dish, the particle will start rolling in one arbitrary direction if it's a spherical particle, okay? So this is an active particle, okay? Now, Denis Barthelot in Lyon has studied what happens if you have many of these particles. So this instability was known since 19th century, okay? But if you have many of them and you go above a threshold for one particle, they all start to move and of course interact at the bottom of a dish, rolling. And you can see that they move together. And then before he sees homogeneous fluctuating liquid, so to speak, moving liquid, he actually saw configurations with typically one very dense band with a long tail, which you could argue, and he argues certainly, has to do with Vicsek bands. But you know, this is a system in which the particles are in liquid. We could discuss how well is this represented by Vicsek thing. Other systems are the systems of a type of granular systems, shaken granular systems. So here you can neglect the air. So Sriram Ramaswamy and us in Saclay also studied such systems. And there are cases where you do see bands, okay? You see bands mostly if you run a very, very faithful model in the computer, because you see the bands easily if you have at least one of the directions which is free, you know, some annular geometry or periodic boundary conditions, so it's better. But these are simulations in which, especially those that Sriram did, are very, very realistic, you know, 3D Newtonian dynamics of things bumping into each other and into the ceiling and bottom. Okay, so everybody believes that these simulations are faithful. If you run these simulations, because you can do this in a computer with periodic boundary conditions, you do see bands. Okay, so to that extent, this is a realistic system, you know, shaken metallic things or whatever, Newtonian dynamics, and it does show Vicsek-like bands. These I tend to believe are Vicsek bands because it's really a dry system. Okay, so other than that, there are all kinds of signatures of coexistence, phase separation between dense and ordered regions and sparse disordered gas. That is rather common, but the formation of clean bands like in Vicsek, not so common. But the general framework of coexistence in a dry setting, and even in wet settings also, that has been observed, yes. Sorry, cross band, no. I mean, you need a very large system. You need larger systems. It's even harder. I'm sure in those granular things, if we were to look for, I'm not so sure. I'm not sure, but yeah, no. Coffee, whatever it is, tea, coffee.